In this video, we're going to be talking about strategies that you should use when solving kinematics problems and really any type of problems that you encounter in physics. We're going to learn a general technique for approaching problem types, but we're going to specifically apply it to kinematics problems using the equations that we've developed for kinematics and the graphing techniques. So let's get started by looking at the specific question we're going to be considering. A jet takes off traveling 1.2 kilometers down the runway, and after reaching a speed of 226 kilometers per hour, or 140 miles per hour, find the following values. The magnitude of acceleration, which we're assuming is a constant acceleration during the jet's takeoff roll, and how long it takes for the jet to reach takeoff speed. We're honestly not given a whole lot of information in the problem itself. Notice that we have two values, 1.2 kilometers and 226 kilometers per hour. We're technically given a third value too, but it's unuseful. That 140 miles per hour is the same as 226 kilometers per hour. It's just we're not going to even use that because it's not useful units. We're not working in the metric system if we're working in miles per hour, and we want to keep our response in the metric system. So we're going to use the kilometers per hour value along with that kilometers distance that we're given. How are we going to solve this with just two numbers? Well, the first thing you should do when you get to a problem, instead of just plugging away and writing down an equation and diving right in, you need to think through the setup of the problem. And that's where we're going to start. We're going to set up how we're going to solve our problem. And the first thing we're going to consider is a diagram of the problem. And that brings up an important question. When we draw this diagram, are we considering the movement of this object from the object model perspective or the system model perspective? Now, what does this mean? If we're using the object model, we're assuming that the thing that's moving is either a single point or a rigid body. When I say it's a rigid body, what I mean is that we assume all parts of the system are moving together with the same motion, or at least we can assume that the system is moving together with the same motion. Think about your car, for instance, especially the body and the interior of your car. When your car is rolling down the road, all points inside the car, on the car's body, the rear view mirror, the steering wheel when it's not moving back and forth, right? All parts of your car are moving together at the same rate. So we would consider the parts of your car that are moving together to be a rigid body. And we could pick any one of those points to represent the motion of the car. For example, I could pick the rear view mirror, a point on the rear view mirror, to be the point from which I'm observing the motion of the car. And that rearview mirror is going to stay in the same position relative to the rest of the car. Not all objects move like that though, and sometimes we need a system model instead of an object model. A system model applies when there's internal movement within the system itself, and that internal movement actually matters. We need to choose a point that is representing the center of the system instead of just a point on the system. Think of a jogger. There's a lot of moving parts on a jogger. And if you were to pick a point on a jogger's hand, you would get a lot of back and forth motion as their hand moves back and forth as they're running. But you're not going to just be analyzing the motion of the whole jogger down the road. And for a jogger, you may have to choose a system model instead of an object model. Another way to think about this, in an object model, you can pick, like I said, any point on the object to be the point that you're analyzing because all points are moving at the same relative to one another. For the system model, the only point that will work to analyze its motion of the whole object is the center of mass. And we'll talk a lot more about center of mass later and how you calculate the center of mass. But in a system model, if you want to measure the movement of the object, you have to choose the center of mass, and then it will approximate the object model because you could just consider that one point for the moving object. And then if you move away from that center of mass, which oftentimes we will do in problems that involve systems, you're going to find that the individual parts have their own internal movements within the system, and you have to track those movements differently, not exactly using the kinematics that we're using for the whole object, okay? So for a moving airplane, are we assuming that the airplane is essentially a rigid object, or is it an object that has a lot of moving parts that we're going to have to account for individually because their movement is going to affect the motion of the plane forward? We're actually going to assume that we're dealing with the object model. Now, again, there are obviously moving parts on a plane, but we're not considering those. We don't care about the motion of moving parts, and essentially we're going to picture the plane as an essentially rigid object, okay? So here's my model, my diagram that I'm going to draw. Here's the plane at the beginning point, the plane just before takeoff, and I can pick any point on the plane that's the same in both pictures, and that's going to be the distance that it travels, as long as I'm choosing the same point on the plane in both places. So here I'm representing the distance the plane moved down the runway. The next thing I'm going to do is label any quantities that I need to put into this drawing. I'm also going to note that as I label the quantities, I'm also going to include values and units. I'm going to include the units of the values so I know exactly what's happening in my diagram. Right away, I'm going to discover that I know two more values from this problem than are just given to me. So in addition to the 1.2 kilometers and 226 kilometers per hour, I also can assume from the way that this problem is described that I know that the plane starts at 0 kilometers, because we're asking 1.2 kilometers down the runway from what? It's pretty obvious that that's the starting point of the plane. I'm also going to put that 1.2 kilometers in my drawing. If I were being really correct, I could put 1.20 kilometers. That extra zero is important. And I will account for that later. But for my diagram, I don't have to be really super careful about that. I just don't want to forget that that extra zero is there. Here's the other thing that I know. If my jet is taking off and attaining a certain speed, I can assume from the way the problem is worded that this jet started at 0 kilometers per hour. It must have started at rest and then took off by speeding up down the runway. And I know that from experience with airplanes that usually airplanes come to rest on the runway first or are moving at a very, very slow taxiing speed, and then they speed up to take off. I know that my final speed at takeoff is 226 kilometers per hour. And then one other thing I can put on my diagram, just so I remember, is that there must be some kind of acceleration happening if the speed is changing by that amount. So I'm just going to label that there is acceleration, even though I don't know the value of the acceleration. I could also note, if I wanted to, somewhere on my diagram that there must be time passing. I'm just going to assume that that's happening without noting it. But it's important to note that there is time passing, and I don't know how much from what's given in this problem. So if I need a time value, I'm going to have to calculate it. There are two steps left to setting up this problem, and both of them are mathematical. The first thing I'm going to do is consider how my quantities are mathematically connected. And the way that I'm going to do that is by considering what equations I know that relate the values in my problem to one another. In this case, I'm going to pull in the kinematics equations because this is obviously a kinematics problem. All right, that's the title of the lesson. But I need to consider how velocity, acceleration, time, and position are all related, and that's what my kinematics equations tell me. Which of these kinematics equations am I going to use? Well, if I look at my problem, I'm looking for the magnitude of acceleration, and if I know the velocity at the start, the velocity at the end, the distance at the start, and the distance at the end, which I have listed all in my diagram, that's going to be this equation, my velocity, acceleration, distance equation. And then the second part asks how long it takes to reach takeoff speed. How long is time? So I'm going to need one of my two time equations, but I don't have all of the information I need in either of those equations. We're going to see graphically, by the way, in just a second, how I knew that I could use this velocity, acceleration, position equation for the first question, and how I'm going to pick for the second question, I'm just going to say as I look at this problem, I recognize I'm finding acceleration in the first part, and then which is the easier of the two equations left to use to calculate time in the second part. And for me, it's no contest. The equation that only has one time variable in it, not a t and a t squared, is probably going to be easier to use. One more note. I knew I was going to need to choose two equations here because I'm being asked to calculate two different values. So I wouldn't be able to do that just using one equation with one unknown. If I have two unknowns, I'm going to have to use two equations to get at those unknowns. You should never have to use all three equations though, because of the way that we derived these. You're going to find that by just combining two of these equations, you should be able to find all of the unknown values that you need. And one more note, I could have chosen that second equation if I wanted to. I really could choose any two of these equations as long as I didn't have two unknowns in both of the equations I selected. So I wouldn't have been able to choose the first two equations because both of those have two unknowns. Acceleration and time is in both of those equations. However, if I select the last equation, I could select either of the other two to solve. It's actually rare that there's just one way to solve a problem. All right, so I'm just going to put those two equations I've chosen over to the side for now in my setup phase, and I'm going to do the last part of setup, which is creating graphs showing the mathematical connections, because this is going to really help me understand what's happening in the problem. What I'm going to do is take that number line in my diagram where I show the position, and I'm going to consider that position either over time, with time as the x-axis, or along with velocity as the y-axis and my position as the x-axis. And the reason I'm doing that is because I'm going to analyze this in two dimensions, and by analyzing it in two dimensions, I can compare two values to each other using my kinematics equations. And that's what graphs do. They help us compare two values as they vary because they're variables. All right, so let's continue by putting some graphs up here. First of all, let's consider the velocity time graph with acceleration. And I'm going to consider what points I know on this graph and whether I'm able to calculate the acceleration given the points that I know. Well, I know 0, 0 is one of my points. 0 time and 0 speed. Okay, that's just the frame of reference that I've set is such that I'm starting at the 0 point. It's also important to note that I've set this up so that to the right is the positive direction. So as the plane moves to the right, it's going to be gaining position in the positive direction, and the velocity is going to be positive as the plane moves to the right. As it accelerates to the right, the velocity is going to increase in the positive direction. It's going to become more and more positive. That's part of what I've defined for this problem. I could set it so that to the right is negative, but that wouldn't make a whole lot of sense in this context. Okay, so I've got my 0, 0 point on my graph, and my graph shows increasing velocity because the plane is moving to the right. What other point do I know? Well, actually, I don't know the entirety of another point. I know that some time passes, and after some time, the plane is moving 226 kilometers per hour. That's what I'm given. So I don't know that time, and I don't know the slope of the line, the acceleration. I can't solve anything on this graph with two unknowns. Now I'm just going to bring in another graph here because this is the easy one to understand, the position time graph. And as my plane moves along the runway, it's increasing in speed, which means that it's going to increase the rate at which it's gaining position. That's why this is a parabolic graph. Do I know points on this graph? Well, I sure do. I know that 0, 0 is one of my points, and this time it's 0 time, 0 position, 0 distance. And the other point that I know is some time, t, and 1.2 kilometers on my position time graph. Once again, I can't solve this because I don't know the acceleration and I don't know the amount of time. There's two variables, two unknowns. And that prevents me from using my position, acceleration, time equation because there are two unknowns in that equation as well, and I can't solve an equation if there are two unknowns. So what equation does that leave? Which equation does that leave, and which graph? Well, it's the velocity, acceleration, distance equation and its associated graph. So here I have that graph, and I would just point out that this is the graph that probably is the most obscure, the least helpful in understanding motion. You're very used to thinking about how quantities change over time because we exist in time and we think about time all the time, right? But with velocity and distance, you don't really consider very often how things change over distance. So of all of the graphs, I would say this is the one where if you feel like when you draw this out, it's not really giving you any information that you can use to paint a picture of what's going on. The reason is because you're not used to picturing velocity over distance. But we can get some important information here. I'm just going to plot the points that we know. We know 0 kilometers and 0 kilometers per hour is one of our points. And then we also know 1.2 kilometers. At that distance, the plane is moving 226 kilometers per hour. So we have our reference point, and we have our point where we know that the plane is moving a certain speed. We have 4 different values that we know that we can plug into an equation. And if you look at the equation on the left, we know 4 of those 5 values. There's only one value that's unknown, and that's acceleration. This is what you're looking for when you're solving these problems. You're looking for a technique that gives you the things that you need to know, except for one unknown that you need to solve for. I also just want to take a moment to point out that this is one of the types of problems that we encounter in physics. This is an idealized problem from a textbook. And in idealized problems, we're usually given 2 points for which we know all of the information, and we're asked to assume all of the rest of the motion from those 2 points. Now keep in mind, this is very different from data that we collect in experimentation ourselves, where we have a whole set of points, and then we graph those points to try to find a relationship between all of them. The techniques that we can use here can rely entirely on these motion equations that we have and just plugging in the 2 points that we know to find the value that's unknown. And that's what we're going to be doing here. I just wanted to point out that this is a very specific type of problem. I call it an idealized problem because we're assuming that the motion between the 2 points that we know is happening the way that we would expect from the kinematics equation. And we never actually look at the rest of the data to see if the motion actually was happening that way. All right, now let's solve the first equation now that we have this all set up. We're going to move from the setup phase to the solve the problem phase. And in this phase, we're just going to do the math for quantitative problems like this. Quantitative problems, again, are numerical problems where we're looking for mathematical relationships between objects. We're going to run into other problems that are qualitative, where we're asked to just describe something, make a prediction about something, and explain why your prediction is probably correct. Okay, so that's what a qualitative problem is, and you'll need to do some of those as well. You'll have to make sure that those qualitative predictions that you make are justified based on physics models and physics theories. You have to use your knowledge about physics to prove that what you're saying is a valid prediction. And then honestly, there's a lot of problems that require you to do both, to use both math and then based on some result that you calculate, extend that result further by explaining and predicting based on that result what's going to happen. So this is what the solution phase is like. You're either going to be solving a math problem or writing based on what you've set up. In this case, we're going to be solving a math problem. So let's solve the math problem on the left here by plugging in the values that we know. What are the values that we know? Well, we know 0, 0 for our initial velocity and our initial position. Now, this is something that oftentimes happens in problems because a lot of time the reference point of the problem is very intuitive, and that 0, 0 point that you choose at the beginning of the problem causes values to cancel out of your equation. And these values would make this equation more complicated. Look at what I can simplify this equation to become. Now it's just Vx squared equals 2ax times the x position. And this is a much easier equation to solve than the one I had before. And I just plugged in my 0, 0 point. Now there's not just one way to proceed from this point. I'm just going to consider that I'm going to be solving this equation for acceleration. And now that I've simplified this by making those terms go to 0 that I knew were at the reference point, I'm going to solve this for acceleration to get acceleration on a side by itself. It's pretty easy. Acceleration is just going to be v squared divided by 2x in this case, because I'm just moving the 2 to the other side by dividing both sides, and then moving the x to the other side by dividing both sides. So this is going to be the expression. Now, could I have plugged in my other point first and then simplified? Yeah, that would be another valid way to solve this, but I think this is a little bit cleaner. At this point, I'm going to plug in my known values. Final velocity is 226. That's going to be squared in the numerator. And then my x value, my position, is 1.2 kilometers. Now, I'm just going to notice I'm keeping everything in kilometers and hours for now. You could convert those right away. We'll talk about converting values. You could convert those before you work the problem. That would be a smart way to do things. I noticed that everything is in kilometers and in hours, though, right now in my problem. I don't have any other units for my speed, distance, or time. So I'm just going to leave everything in kilometers and hours as I solve this. I'm going to go ahead and do the math. I need to square 226 and then divide by 2 and then divide by 1.2. And when I do that, I find that my rounded result is 21,300 kilometers per hour per hour. Now, that seems like a large number, but if you think about what we're saying there, if I were traveling with this acceleration for an hour, which is a long time, I would have attained 21,300 kilometers per hour. So that's not a very intuitive label. We're going to deal with that in a little bit. But this is my response. So you may be wondering, why did I round off where I did so that I have a rounded off value in the hundreds place? It's because in the problem, my numbers that were given to me all had 3 digits that were measured significant digits. So notice that 226 kilometers per hour has 3 measured digits that are not zeros. 1.20 has 3 measured digits as well. 1 and 2 in 1.2 are measured, and that extra 0 that's tagged onto the end didn't have to be placed there. The only reason it was included is because somebody actually measured that extra 0, so it's included in the number. So none of those are placeholder zeros. Those are all significant, and that's why I included 3 values in my final rounded result, and then I just put those 2 placeholder zeros at the end, 21,300. Now here's what is interesting about this. When I use that value, when I calculate anything else, I'm going to want to go back and use the unrounded value because that's going to give me a better calculation. But then when I report my final value for A or B, I want to make sure that I rounded off the correct amount. And that way, whoever's looking at this value knows how precisely measured the quantities were that were used to calculate this. Okay, so that's why we round where we do in physics. It's called rounding to significant digits. I'm not going to spend an awful lot of time on it in this lesson, but it is something that you may want to pay attention to. Because it is sort of important to know why we round things where we do to report a certain amount of precision in our measurements. All right, let's move on to the next part of this. And to do that, I'm actually just going to move my graph over and record above that graph the acceleration that I just calculated. Because that acceleration is the slope of this graph. And if I know 1.00, I know the y-coordinate of the second point, 226 kilometers per hour, and I know the slope of the graph. Can I solve for that one unknown point? Well, I sure can. First of all, let's simplify by taking into account our reference point. My initial time is 0, but that doesn't actually show up in this equation anyway because t, remember, is the time interval. So I'm always assuming that the initial time is going to be 0. But the initial velocity is also 0, so I can set that initial velocity value to 0 right away and simplify my equation. Well, that makes this equation very easy. Vx equals at, and then I know a, I know v, I'm solving for t. I'm going to get t on a side by itself. That's vx over ax. And then I'm just going to plug in the values I know for the velocity and the acceleration. And then it's as simple as dividing those two values to solve. Now that looks like a really small amount of time, but keep in mind, once again, because I'm using the units of time that were in the values that I plugged in, that's a time in hours. And we would expect that this plane is probably going to accelerate to its speed on the order of magnitude of like seconds instead of hours. So 0.0106 hours is probably going to be a correct value. We would expect it to be small. Also notice once again that I recorded this with 3 decimal places of precision after my leading placeholder decimal. So that first 0 is just a placeholder in the tenths place to show how small my number is. And then after that, I'm writing all of my significant values that are actually like measured values, 0.0106 hours. And that's it. We're done solving the problem and on to our last step, which is to reflect on our solution. Now, we've already done a little bit of this. First of all, when we reflect on our solution, we need to make sure that our units make sense, and then we're going to make sure that the values connected to those units make sense. Now, we've already considered whether these are correct values, like my first one was so big, should it be that big? My second one was really small, should it be that small? We'll do that again once we do some dimensional analysis and some unit conversion to change these to SI standard units. Instead of kilometers per hour, we're going to change everything to meters per second, meters, seconds, the values that we're used to considering, we're used to working with. So the first thing we're going to do is ask if our units make sense, and we're going to do something called dimensional analysis to do that. We would expect an acceleration to be reported in a unit of distance divided by a unit of time squared. Kilometers per hour squared is that. It's distance over time squared. And that means kilometers per hour, okay? And we would expect the unit of time to just be in like hours or seconds, just have a time label without any distance labels. So how are we going to make sure that what we calculated is correct? We're going to do something called dimensional analysis, where I'm just going to get rid of all of the numbers and just write the unit labels of the numbers within the mathematical expressions that we were using. So I'm still going to square kilometers per hour, and I'm still going to divide by kilometers, and I'm going to see if when I just do the mathematical formulas on the unit labels, I end with my intended unit label. I end with a unit label that actually describes the variable that I'm trying to describe. So if I take kilometers per hour and square it and then divide that result by kilometers, do I get kilometers per hour squared? Well, if I square something that's being divided, I have to square the top and the bottom of the fraction because the square actually distributes in. So it's going to be kilometers squared per hours squared divided by kilometers. And then you can do this a couple of different ways. One of the easiest ways to consider when we divide a fraction by a value is put that value over 1 and then invert and multiply, right? So it's like we're dividing by kilometers over 1. And when you divide two fractions, you flip the bottom one upside down and multiply across. Any way that you think about this, that kilometers is going to cancel out one of the kilometers squared on the top. Kilometers squared just means kilometers times kilometers, and I'm canceling it out with the kilometers in the denominator. So I'm just going to show that I'm canceling those out, and you'll see that what's left there after I've canceled units is kilometers per hour or kilometers per hour squared. So by dimensional analysis, I know that this equation should have worked to calculate an acceleration. What about on the other side? Once again, I'm just going to bring down my unit labels with all of the math that was being done. And here I had my kilometers per hour squared acceleration in the denominator and kilometers per hour speed or velocity in the numerator. Again, when I divide a fraction by a fraction, it's the same as if I flip the bottom fraction upside down, I invert it and multiply across. I'm just going to actually show that here. So I have my kilometers per hour times the inverted denominator, which in this case is hours squared per kilometer. Notice that when I multiply these, I have kilometers in the numerator and denominator, so those are going to cancel. And then I have hours in the denominator and hours squared in the numerator, which is hours times hours. So one of those is going to cancel, and I'm left with just hours. So by dimensional analysis, I know that the second equation worked to calculate a time value because that's what I had left. And if I ever calculated something unexpected, like let's say in the second one I had hours kilometers or something, hours times kilometers, I would have to go back and check my math because something went wrong in that equation. All right, now one other thing that we can do with dimensional analysis, we can actually change our unit labels to something that's more standard. And the expectation is, in general, you're going to report values using standard units. Meters per second squared. Meters and seconds are the international standards for distance and time. Okay, so I need to change this from kilometers per hour squared, which is something I can't even visualize, to meters per second squared, because that's a much more easy to picture value. And to do that, I'm going to use this handy prefixes table. This is a prefixes table that's available on your AP Physics 1 equation sheet. And do you notice any prefixes that are used in the values that I have in my label? Notice that kilo is attached to meters to make kilometers. What does kilo do? Well, kilo multiplies my base value times 10 to the third, or 1,000. In other words, 1 times 10 to the third meters, 1,000 meters, equals 1 kilometer. Now, let's just think about that expression for a second. Those two things are equivalent. 1,000 meters, 1 kilometer. What would happen if I divided those two values by one another? Let's say I take 1,000 meters divided by 1 kilometer. And keep in mind, I'm using unit labels to denote something important here. These values are the same according to that equation up above. What happens when I divide two values that are the same? What if I were to flip this upside down and divide 1 kilometer by 1,000 meters? These values are the same, so these should be the same value. And what is that same value? Well, if I divide something by the same number, I always get 1. And that's why these are called unit conversion factors. Unit, 1. This is a unit conversion factor when I multiply by two values that are the same because their label makes them the same. And then I can use these unit conversion factors to cancel out unwanted units to turn something into a value with different units. Let me show you how this works, because that was a mouthful, but I think I can show you better than I can say it. So I'm going to take this unit conversion factor we just developed, and let's multiply it into our value that we calculated before. Hey, what am I multiplying 21,300 by when I multiply it by a unit conversion factor? I'm actually just multiplying by 1, and I'm going to account for that. I mean, okay, if you look at it, I'm actually multiplying by 1,000, right? But I'm going to account for that by changing the label every time I multiply by a unit conversion factor, and that's going to keep the value the same. Even though the base number is changing, the unit label is keeping the base number the same. All right, so I'm going to multiply by 1 times 10 to the third meters per kilometer. Notice what happens. I have kilometers in the denominator and in the numerator, so kilometers are going to cancel, and now I'm left with meters per hour squared. But I don't want hours, I want seconds. How am I going to convert that hours to seconds? Well, I can multiply by a conversion factor that we all know. There's 1 hour for every 60 minutes. 1 hour and 60 minutes are equal. So I can multiply by this as a unit conversion factor. Is this what I need to multiply to change it to meters per minute? Well, let's see what happens. My hours is going to cancel out just one of the hours in hours squared. So what do I need to do? I need to multiply again by the same conversion factor. Anytime you have a square unit, you actually need to multiply by your conversion factor twice to get rid of that square. If you have a cubic unit, you have to multiply by that same conversion factor 3 times to get rid of the cubic unit. So here I'm going to multiply by 1 hour per 60 minutes again. I don't want meters per minute though, I want meters per second. How am I going to accomplish that? Well, I can multiply by 2 more conversion factors, 1 minute per 60 seconds. That'll cancel out the first minutes, that'll cancel out the second minutes, and look what I'm left with. I have meters in my numerator, and I have seconds times seconds, or seconds squared, in my denominator. Now I'm actually going to do the multiplication across. It's 21,300 times 1,000 divided by 60, divided by 60, divided by 60, divided by 60. Or I could just multiply all of those 60s together first, and then divide by that value when I multiply those all together. And my end result is 1.64 meters per second squared. That is a very reasonable result for a somewhat fast acceleration for a jet. If you consider that gravity pulls you toward the ground at about 10 meters per second squared, we're going to learn very precisely it's 9.80 meters per second squared. Gravity accelerates things pretty quickly. If you fall from any height, you can hurt yourself, even if it's not that high up. Something that's about 2/10 the size of gravity is a pretty fast acceleration. 2/10 or 1/5 the size of gravity. So this is a reasonable answer. And again, I'm asking that question. Is this a reasonable response? Yes, it seems to be. Okay, now let's look at our time value. What is 0.0106 hours in seconds? Well, I'm going to need to multiply by some conversion factors. Can I use the same conversion factors that I used before? 1 hour is 60 minutes, so 1 hour divided by 60 minutes. So look what happens. Do I get to cancel anything out here? If I were to multiply by 1 over 60, notice that my hours would be squared and it'd be divided by minutes. This would jumble up my unit labels, and I can't use this. So what am I going to do? Well, remember, with unit conversion factors, I can just flip them upside down, and I'm still dividing by the same thing, because 60 minutes is 1 hour. So here I have 1 hour in my denominator, and that's actually going to cancel with the 1 hour that's in 0.0106. Okay, now I don't want this in minutes, I actually want this in seconds, so what do? I need to multiply by another conversion factor. Hey, do I have to multiply by 60 minutes over 1 hour again like we did before? Well, the only reason we multiplied by the same conversion factor was because in the previous one we had hours squared. But here we just have hours, we have one of them, and it's already canceled off. So I can just go ahead and multiply by my next conversion factor, 60 seconds in 1 minute. And then I can cancel out minutes, and I'm left with a result in seconds. So I'm going to multiply 0.0106 times 60 times 60, and that's going to give me 38.2 seconds. Is that a reasonable response for how long it might take a jet to take off? Well, if you've ever taken off in a jet before, it doesn't take quite a minute to get up to speed, but it does take several seconds, many seconds to get up to speed. So 38.2 is a reasonable response. I'm just going to go ahead and replace my 0.0106 hours with that 38.2 seconds. And now I have my values in standard units. What are the other parts of reflecting? Ask yourself, is this calculated result realistic? And I think we asked ourselves that question as we went along. Yes, our results are realistic. They make sense with the problem. I feel like we did a good job calculating the correct answers in this problem. And then the last thing we have to ask is, did we follow the rules of physics or did we break any rules? Well, kinematics rules are pretty straightforward. We were moving with a constant acceleration, so I used equations only that accounted for that acceleration. Notice I didn't try to use the constant speed equation. That would have broken the rules of physics, because if I'm accelerating, I'm not going to be moving at a constant speed. So I didn't even consider that as one of my options for my equations. I only considered equations that accounted for acceleration along with distance, time, and velocity. And that's how you solve kinematics problems.